Hi, this is the lecture video for week 4, module 1, and we're going to cover sample size in module 1 of week 4, and the slides for this are a bit, it's a large slide deck, so I'm going to break it into two parts, and in part 1 I'm going to cover slides 12 through 29. And I've started at 12 because all of this with regards to sample size and power should be a review from Clinical Research 517 and 518, which you had with Dr. Giratek the past two semester terms. So I'm just going to review basic concepts and elements with regards to sample size and power, and then also run through some examples. So before you can calculate a sample size or perform a power calculation, you have to understand the important elements that are required for the sample size and power. So you need to specify first a hypothesis test on a parameter. So basically, what statistical test will you do? What type of data that do you have for your study? Next, you're going to want to specify that significance level. So what are you setting your alpha at? Typically, that's standard set at 0.05. Next, you want to specify the effect size. So this is the difference that we expect to see between the groups. This is typically determined from a lit search and prior background studies. You also want to obtain historical values or estimates of other parameters needed to compute your power function. So if it's a mean with regards to continuous data, what are those historical values, or if it's proportions. And again, this also will be determined by that literature search or background research. Next, you're going to want to specify the target value of your power. So typically, we think of this as 80% power. So what are the elements then? And we're gonna we have an example listed here. We're gonna go through each of the elements presented in this example. So we chose a study for 313 subjects in each group in order to have 80% power to detect 33% reduction in the recurrence rate from baseline rate of 30% with a significance of 0.05. And this is a two-tailed test. So breaking this down, we're going to start with that alpha level. So 0.05, two-tailed. This is our standard definition of clinical significance. Maximum likelihood of making a type 1 error. So there's a 5% chance of rejecting the null hypothesis when it is actually true. Another way to think of that is if the null hypothesis states there is no difference, then this is your chance of stating that there is a difference when none actually exists. Next, within the example is 80% power. So the power is the inverse of beta, so this is our likelihood of making a type 2 error. So power equals 1 minus beta. This is the chance of failing to reject the null hypothesis when it is actually false. So this is our type 2 error. 0.2 is what this is set at. And 1 minus 0.2 gives us that 0.8% for our power. So if the null hypothesis states there is no difference, then this is your chance of finding no difference when one actually exists. So just reviewing power a little bit more here, this is the chance of observing an association or difference of a given effect size or greater in a sample if there's an association or difference actually present in the population that you're looking at in your study. It's actually that probability of detecting a real difference between your groups. An increase in sample size or a bigger difference between the groups generally is going to increase your power. An increase in the standard deviation, also known as the variability, or an increase in the significance level reduces your study power. So what is that difference then? So delta is what we refer to as the effect size. The difference you expect to see between your groups that is clinically meaningful. And you can see here the depiction on our on the graph. So in our example, they want to detect a 33% reduction in the recurrence rate from a baseline rate of 30%. So typically you would look at this and say that it's the difference between the two, but the key there is that the baseline rate is 30%, and you're trying to detect a 33% reduction from the baseline rate. So we have to take 33% times the baseline rate to get that delta. So we take 0.3, you can see here in the example, we take 0.3 times 0.33, which is our reduction. So 0.099 is our absolute amount of reduction. And then to get that estimate for the treatment group then would be 0.3 minus 0.099 is 0.2 with the treatment group. And what you can see then is you could subtract this one from 0.2 from 0.3 is a 10% difference. So we expect a 20% recurrence in the treatment group, 30% in the baseline group, delta of 10%. So power and sample size calculations can actually differ depending on the type of statistical test that you're using and the type of data that you have for your study. So that's just something to keep in mind. It also can, the calculation, the amount that you get for your sample size can differ depending on which program you use. Whether you calculate it by hand or whether you use a different calculator might have slightly different variations with regards to the sample estimate. Power and sample size estimates are basically just a best guess. You do need to account for dropouts and missing data with regards to your sample size. Typically for prospective studies, you estimate around a 20% dropout rate. And then we're always going to assume that there's one outcome. If you have multiple outcome variables, then this can be problematic. And remember that we typically power on our primary endpoint. So our primary endpoint, our primary objective. So this just lays out with regards to the type of data that you have for your outcome variable, the type of data that you have for your predictor variable, what statistical test will be appropriate, which is going to help you determine which statistical calculator to use and which equation to use when you're estimating your sample size. So you can see if you have a dichotomous outcome variable, so this is considered a categorical variable, and you have a dichotomous predictor variable, the appropriate test would be a chi-square test. If you have a continuous outcome variable and a dichotomous categorical predictor variable, the appropriate test then would be a t-test. If you have a continuous outcome and a continuous predictor, then appropriate would be a correlation coefficient. So with continuous data, we are basically comparing two means. So some examples here, if you have blood pressure measurements that you're comparing between a treatment and placebo group, or perhaps it's exercise time between two groups of people, so maybe men versus women, or if you're comparing the heart rate between two groups. So those are all examples of continuous data where you're comparing the means between the two groups. So in this case, t-test would be appropriate. So a t-test is when we're determining the mean value of the continuous outcome variable in one group, determining if it differs significantly from another group. When we're using a t-test, the effect size and the variability is estimated from previous studies. So again, you're going to do a lit search to try to determine the effect size that you expect, and then also the variability. So variability is the standard deviation. Occasionally, if this is not available, one might choose to do a small pilot study. And then we have to consider the standardized effect size with regards to t-test. So this is the number of standard deviations different that the experiment is designed to detect. So this is calculated by the effect size divided by the standard deviation of the outcome variable. So again, laying out the steps for sample size, we have our hypothesis. We start with our hypothesis, then determine our effect size, estimate our standard deviation. Again, typically both 2 and 3 would be determined from a literature search and prior studies. And then you would calculate your standardized effect size and set your alpha and beta. So the standardized effect size, as you can see, the bottom portion of that that equation there. And this here is the equation that if you were calculating this by hand, that you would use for determining a sample size estimate for a t-test and continuous data. So the standardized effect size is determined the treatment difference, again, divided by standard deviation, just like we said in the last slide. So again, here's that equation. So Z alpha and Z beta are typically set for us, and these are based on our alpha and beta, or power in this case. So our Z alpha, because our alpha is typically set at 5%, is set at 1.96. Our Z beta for 80% power would be 0.84. There is also a t-test shortcut that you can utilize, but the assumptions in order to use the shortcut is that you have to assume that there's more than 30 subjects that will be studied. The power is 80%, beta is 20%, and then the alpha is 5% and two-sided. So in this case, the sample size, and again, the number that you get is per group, would be 16 divided by that standard effect size squared. And this assumes equal variance in equal sized groups. Things to keep in mind is as that standardized effect size gets smaller, a larger sample size is needed. A sample size needed to detect one standard deviation difference with 80% power is 16 in each group, or 32 total. A sample size required to detect a standardized effect of 0.5, so that would be 16 divided by 0.5 squared is actually equal to 64 per group, or 128. So one thing I wanted to mention just before we get into the t-test example is that the t-test is a remarkably robust study, and this can actually be used for almost any distribution unless the number of subjects is small. So by small we mean fewer than 30 or 40 subjects, or in the case if there's extreme outliers. The standard effect size is unitless, so it doesn't have any units attached to it. And this makes it possible to estimate a sample size when an investigator cannot obtain information about the sizes of different variables. So for example, if we have a 10 milligrams per deciliter difference in serum cholesterol levels, which there is a standard deviation in the population of 40 milligrams per deciliters, this would equal a standardized effect size of 0.25. So again, dividing the 10 by 40 gives us that 0.25. And again, keep in mind, larger standard effect size equals smaller sample size. And effect size that are very small are often difficult to detect. So you would need a very large sample size to detect a small sample size. And typically small effect sizes are not very clinically important. So that's just some things to keep in mind with regards to the t-test. So now we're going to run through a t-test example. So here we have a randomized trial of the effects of 2 cholesterol-lowering drugs on LDL. So LDL is the bad cholesterol. And the difference of mean LDL levels of 10 is relevant. All right, so that's the delta that we expect. The standard deviation then is expected to be 15, and this is based on prior studies. Our alpha, it's a two-sided alpha. Alpha standard is 0.05, beta 0.2, and again, standard deviation is set at 15. So the sample size, if you do this calculation by the shortcut method, would be 16 divided by our standardized effect size calculations. That would be 10 divided by 15 squared, and then divide 16 by this number then. So what you actually get there is 35 per group. So that would be a total sample size of 70. So I want to actually repeat this then on the sample size calculator within JMP so that you can actually compare the two. And this is actually, let me go to my JMP right here. So everyone hopefully still has JMP on their computer from 517 and 518. I will post within week 4 the instructions for downloading or updating the license if you still need to do that. You should have access to it as a Campbell student still. And if you have any trouble, even with the directions that I post, my next recommendation would be to contact the help desk and let them know that you need it for your class. So for sample size calculator within JMP, you're going to go to the Design of Experiment, DOE, tab up here, and then scroll down to sample size power. So this is a t-test. So what we're going to be looking at, testing 2 sample means. So we're going to click on that. All right, and let me pull my slides back up so I can see, and then pull the. All right, so I can see both of them. So then what we're going to do is basically plug in the important values in order to determine the sample size that we need for this. So our alpha is 0.05, and you can see that's already entered in there for us. Our standard deviation we know is set at 15 in this case. Our extra parameter, that stays set at 0. The difference that we expect to detect, so that's our delta. This is going to be 10%, or I'm sorry, 10. We're going to leave sample size blank because that's what we're trying to determine, and then we want a power of 0.8. All right, and you can see here it tells you exactly what to do as far as you need to supply 2 values to determine the third. So in this case, so let's say if we were determining, if we had a sample size and we just wanted to determine power, we would enter sample size and then it would give us power. But in this case, we want to know to get 80% power, what sample size do we need? All right, so hit continue. And you can see here that for this example, we need 73 total sample size. And you can see that just like our hand calculation here, where we had 35 per group, 70 total, that 73 is close to that, comparable to that. And you can see here that what this calculator spits out then is the total sample size. If you want the per group estimate, then you divide that by 2. All right, so this is exactly, you're going to do examples within your homework for week 2, both doing t-test continuous data as well as proportions for categorical data. And I want you to do both examples by, or the examples that you have by hand with the actual equations. And then I also want you to check those with the sample size calculator and do screenshots to submit for your homework for this week. So just wanted to mention some situations that require tailoring the calculations with regards to t-tests and sample size. So if you have a paired t-test, or if there's unequal groups, so if you have more controls versus cases, in cases where, again, with the example that we did, the variance was the same, but the variance may not always be the same. And then also if you have one sample when you're comparing to, say, a historical control. These are situations when you might have to tailor that calculation to these specific examples. So this concludes part 1, and we'll pick back up then with part 2.